Okay, so we're going to send our laser through. Now here's what's going to happen. Here's our screen back here that we're going to look at. We're going to send our laser through, and I'm just going to look at different paths of the light. So remember, light's going to bend around a corner. So it's going to bend this way, this way, this way, etc. And we're just going to look at a few beams of the light and watch what they do. So for instance, I'm going to look at a beam of light that travels right through the middle, right to the middle. In other words, if this distance is L, this distance is also going to be L. So since they're traveling the same distance, what should be true when these two waves come together? They add up to each other, right? And so right here, you should expect a bright spot, or what we often call a bright fringe. So remember, if light was a particle, you would expect there to be nothing here, because this blocker would block the light. However, since light diffracts as well as interferes with each other, you actually end up with a bright spot directly behind this. Okay, so that's our first bright spot. Let's look at another bright spot. Let's look at a beam, and I'm just going to redraw this. Depending on what your paper looks like, you may want to just do this all on one. So we're going to look at a beam that comes over here, and a second one that goes right here. So this travels a distance L. And what's this one going to do? Travel farther or shorter?
Farther.
It's traveling farther, right? So we're going to say this one travels exactly L plus lambda. So it's traveling L plus lambda farther. Remember, we already had this bright spot right here. We often call this the 0th order fringe, or the central bright spot. So anyway, this is L and this is L plus lambda. What should happen if light is a wave? They should interfere with each other constructively. So you should expect another bright spot right here. The same thing would happen directly below it, where now this one's traveling L plus lambda and this one's traveling L. And so you should expect another one on the other side.
So
Yeah.
the distance between the two slopes in the first one would change where the bright spots are located? Like the distance? Yeah.
Yeah. And we'll,
The difference between each bright spot and lambda?
no, but you're on the right track. And we're going to go, I'm going to go ahead and derive it. But that concept is right. The concept of what you're talking about is right. Okay, so this we'd call, any guesses on what we're going to call this fringe? First order, yeah. So this would be the first order bright fringe. Okay, and this would also be the first. Now hopefully you can notice, I could draw another one like this. We could call this one L. Now how's this second one going to travel compared to this one? It's even farther, yeah, and we'll say, okay, the path difference of this one is going to be 2 lambda, which means when those two get together, what's going to be true over here? Well, it's going to be another bright spot. And this one we call this second order, etc., etc. Okay, so for every bright spot you get, it's going to be one wavelength path difference greater. Yeah.
They get progressively brighter as you
These are relatively equal in brightness, believe it or not. They would get progressively dimmer, slightly dimmer, but like this would be the brightest one, the one in the middle. These would be pretty close to each other, surprisingly, but they would be slightly dimmer. Okay, so let's look at the black spots, and actually maybe you guys could figure out what's going to go on with the dark spots. What do you think? Let's get a new paper. Again, you might be able to just do this already. So this one's going to be bright. Let's do our first, second, third. First, second, third. And then let's draw a beam like this. So we're going to draw a beam here that travels L. We're going to have a second beam here that travels what?
L plus 1/2 wave.
L plus a half. Now when these come together, you're going to have a wave like this. This one's going to travel a half a wavelength farther. So what happens when they interfere this time? These would be destructive interference, right? So right here, you're going to get a dark spot here. And same thing over here, dark spot. Okay? Any guesses if we send this one here and this one here? This would be L, and what would be this one right here?
3/2.
L plus 3/2. Right. And when those get together, what's going to happen? Nice dark spot. Okay? So you get these alternating fringes. These would be called the first order dark fringe, second order dark fringe, and so forth. Okay? So this is why you get these multiple fringes. And the evidence then is, well, this would never happen with a particle, right? It's inconceivable this would happen with a particle. However, we can explain it using waves because of interference and because of diffraction, both of those. Okay?